Here we go, guys. You should get your warning popping up on the screen. Now, the first question we just had was, now that my audio is working, was, will we be back in class on February 1st, or will it be pushed back the way some other people have been pushed back? The classes that have been pushed back, from my understanding, were pushed back because they are more easy to convert to an online setting than something like a lab. And having tried to teach lab online for the last 2 years, I can tell you from experience that the best we can do for a lab setting, like we discussed last week, was basically a crappy version of Portal. And that's just not acceptable for lab. Now, I myself, as well as many of you guys, probably have concerns about health. And that is why I am glad to be able to say that every single person, both in my Tuesday and Thursday nights, has passed the campus requirement for vaccination. So at least we know everyone's vaccinated. You also will still be required to wear masks, which is going to be not the easiest thing I know to do with goggles as well. But we will do the best we can, okay? Aside from the current situation, the best we can do is try to just keep each other safe. So, you know, we will do our best to distance from one another when we can. We'll wear our masks, make sure that you're vaccinated. If you have any belief that you might be infected, please don't come to class. I would much rather you told me that you were infected and you didn't come to class and gave me the opportunity to come up with some alternative thing for you. Now, please don't use that as a reason to skip class, of course. But you guys should all have access to testing, hopefully. If you haven't, please go online. If you are still living with a group of people, hopefully someone has done it for you and placed an order through the United States Postal Service to get 4 free tests per household. Those are an excellent item to have on hand. Do the best you can to stay safe and keep each other safe. But we are going to be back in class on February 1st, like it or not. That's the situation, okay? And in general, yes, I am going to require you guys to be in person. Now, the advantage to that is I'm also going to allow you to, as I start posting homework assignments more in advance, and as I adjust the due dates, if you complete a homework assignment before the due date, and I'm going to adjust the due dates hopefully in a way that make it possible for you guys to do this effectively, you can churn a physical copy of the homework assignment into me in lab instead of having to submit it online. I'm going to do that, or at least we're going to try that out for maybe the second assignment if we can, okay? And the reason I want to do that is because I know it's not the easiest thing to do still for some people. Turning homework assignments in online, some people struggle with, and I understand. The goal is to make this as easy as possible for you guys to succeed with as few obstacles and hurdles. That is my goal. Now, as far as where I have posted the recordings, I can't tell you where I posted them because I haven't posted them yet. That is one of the caveats to that question. I'd have to have a location where they are already stored, but they will be coming soon, probably within the next day or two, probably tomorrow, because tomorrow will be the day that I really have the time to work on it after my office hours. But it's a great question, so thank you for asking. I would love to know. I would love it if I could be able to say, well, yeah, no, the recordings posted themselves. That would be wonderful. The system's not quite that automated yet. Let's see, make sure I didn't miss any other questions. Okay. Is there anyone who has not been able to find the homework assignment on the main lecture Canvas page? Is everyone able to see the homework assignment? Okay. My next question for you is, does everyone have access to the calendar? Because I've tried to set up the calendar in a way that will answer your questions with regard to when is office hours, when is lab, where is lab, how do I get links for office hours, how do I get links for any other postings I do. Can you guys find the calendar on Canvas? Are my calendar dates showing up for you? Okay, fantastic, good. I'll be honest, it's the first time I've actually made extensive use of the calendar. So my hope is this time having a highly organized calendar for you, that'll make it easier for you to be able to track when everything is going on. Office hour will be the way that it is established now in the syllabus, which is Monday and Wednesday from 3:45 to 4:45. Unless something happens. If, for example, I got a flat tire on my way from work, then I will reschedule my office hour to something else. Now, of course, that doesn't mean try to track down my car and slash my tire. Please don't do that. It's expensive. But that an aside, I will try to hold regular office hours those 2 days. If it is possible, I will also try to schedule other times when I may hold a lecture or question and answer sessions. I am contemplating holding a lecture tomorrow to record chapter 2 and chapter 3.
Professor, I have a question.
Certainly.
On the Canvas, since I got the permission number, I was able to enroll. When I log into Canvas, it gives me 2 course options for this course. Is there a particular one that I have to enter? I just wasn't here that last week in Zoom, so sorry, it's a late question.
Not a problem. Okay. I'm certain that even people who were here last week may be asking that question. I have been trying to rename the courses in a way that makes sense. There should be 2 Canvas pages that are appearing for you. The first one will say Professor Shru's something, 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 and that is the lecture page. And then the other one will say Tuesday, Chem 305 Lab Shru. And that is specifically associated with lab. And I'm trying to do it that way this semester to keep things more organized and straightforward for you. So you don't have to go, okay, this is something associated with lab, but where do I find it on this page? If you go for lab, you go to one site. If you go to lecture, you go to the other site. And that way, hopefully it'll also keep your brains more organized. It's an effort for me to try to keep my own mind more organized.
All right, thank you.
No problem. You got it. Okay, so lectures in general for this class will be on the lecture site. Assignments like homework, things like that will be on the lecture site. Final grades and grades associated with lecture will be on the lecture site. In general, just things associated with lab will appear on the lab website. And I want to do it that way to also make it easy for you guys to know where to turn things in if you need to turn in an assignment. I'm going to give you 2 options for lab and lecture turn in. You can either turn them into me physically, or you can turn them in digitally. The advantage of having both options is if you happen to leave your lab at home and you wanted to turn it in. So say you had the lab for today was due next week and you wanted to turn it in next week, but you forgot it at home. The lab electronically will be due by midnight. And that will give you the ability, if you happen to unfortunately forget your assignment, to have a backup plan of scanning it and submitting it electronically, which is the best I can do. And honestly, it's better than I had when I was your age, sort of thing. So the point being, I just want to make it as accessible and have as many options for you guys as possible. And I hope that works for you. It'll actually make my job a little bit more difficult since everything won't be in one location. Some things will be physical, some things will be electronic. However, I'm willing to take on a little bit more of a burden if it makes it more easy for you guys to succeed. And that is my goal. I will also say, as I make these adjustments, come up with new ways of trying to help you guys succeed, the syllabus will be altered and updated so that you will have these updates stored in a document that actually you can refer back to. That is why the syllabus says at the end of it that this syllabus is subject to change and update without notice, because I like to be able to come up with new ideas to make things better for you guys. Also, with the pandemic ongoing, if there is a sudden spike in numbers, I doubt we'll go back to purely online, but I don't want to say never or anything like that, because you cannot predict what will happen these days. And you can't predict what would happen any days. I mean, it's not like things have gotten that much different. We're not dealing with the Black Death here either. Thank God for sanitation.
For the dry lab, I saw that on page 5 it had, let me see, 3, 5, and 7, but there's no numbers or problems in that page. I had a question about that.
It should be page 8.
So let me take a look here.
Yeah, it should be page 8. Sorry, yeah. But yeah.
So are you looking at the updated one that I numbered?
Yes.
Okay. And then the lab page, what did I actually assign? I know
Yeah,
that there's
it was page 8. I emailed you and I talked to you about that problem.
and I thought I
Yeah.
had gotten it right, but my apologies if I did not. I am trying to make sure I get things right. So it says page 5, numbers 3, 5, and 7. And page 5, when I look at page 5, what do I actually have on the one that I have here? That's the one I'm looking at. What actually happens when I open the one that I posted for you guys? Does it look the same as what I actually have on my computer? So page 5 looks like something that has assignments on it. Oh wait, no, but not, yeah, not the numbered ones that I'm talking about. Yes. Okay, so I need to update that. I will update that tonight. Let me make a note of that. So it needs to be updated on the website. So page 5 needs to become number 8. Yes. Actually, you know what? I'm just going to update that right now. I'm going to make that change right now before we even move on, because that way it will get changed in real time and you guys will be aware of it. Most people will be, at least anyway. Okay, you guys should also receive an email about that change. 8, 10, 11, 12, 13, 14. Yeah, okay. That should fix that. My apologies for not realizing that. I looked at that too fast when I was looking at that. And I am sorry that I did not catch that sooner, guys. And I also apologize, for not realizing exactly what you were telling me, because you were telling me the correct information. My apologies. If you completed it, awesome. I was trying to make it more accessible, and apparently I made it more inaccessible. Best laid plans of mice and men. Okay, are there any other questions before I actually start talking about some material?
I had a question, but I wanted to ask you about it after.
Okay. You got it. No problem. Are there any other pressing questions? Okay, then the next question I have for you guys is, are there any subjects from chapter 1, since hopefully you guys have been at least able to look at the subject titles on the website, or if you haven't, that's okay. If anyone has a copy of the book and has flipped through chapter 1, are there any subjects from chapter 1 that you would like me to cover myself before I move on to chapter 2?
No questions.
Okay, it sounds like chapter 1 is pretty under control for you guys. Okay, then what I kind of wanted to do tonight, my general plan for the evening is to cover subjects from chapter 2, give you guys a good layout on that. I see. And then I will probably have essentially a little lab to cover some topics from chapter 2. Essentially a boost in the direction of that. We'll see. And I see that there are still some concerns about the first assignment. I'm going to grade that one pretty leniently because that one is on me for not having that assignment more solidly put together. I know for a fact, because I have taught from this book before, I haven't used this specific lab manual before, but I have used this book before. I know for a fact that the book assignments and the homework assignments will not have the same issue as long as you guys can actually find the correct edition of the book and make use of those questions from the back of the chapters. That is not going to be an issue. I have zero concerns about that. And then as far as it comes to the physical labs, in lab, in person, those will tend to be the ones coming directly from the lab manual, which is proving to be a burden to upload as a whole. So I will actually break it up into pieces and upload for you guys in essentially chunks of lab, because that way you'll actually be able to access it. It's apparently too large a file for Canvas to handle. Okay, so let's see here. Sharing the screen with you guys, like so. Okay, so what we're looking at tonight in general, and I'm taking advantage of the fact that I have you as a captive audience, combined with the fact that I want to kind of record something that will hopefully become the lectures for chapter 2. So chapter 2 is has the heading of atoms and the periodic table. So as you might assume, that is a rather important topic. Of course, one could argue that virtually any topic in chemistry is going to end up being called an important topic, and it is difficult to separate topics from what is important and what is not important. I'll probably end up saying every chapter is important. However, at least we can say in a chapter, I'm only going to do my best to focus on what I consider to be important topics. So in this, we're going to cover things like atomic theory. That's going to be a relatively brief one because the atomic theory just is kind of a build-up, a lead into a lot of more important aspects of what we will discuss in this chapter. We're going to look at elements and the atomic number, define that for you guys. We're going to look at isotopes. and atomic weight. And yeah, this is the way the chapter is broken down. And I'm trying to follow the way that the book is broken up so that if you are following my lectures and you're utilizing the book is actually an important resource to you and not just another doorstop that you spent money on. My goal is that you guys don't waste any money in this class, or at least that you hopefully don't feel like you've wasted too much. We'll cover the periodic table. We'll talk about briefly characteristics of what we call the groups, because they do have some interesting characteristics. We'll talk about electronic structure of atoms. We will cover electron configurations. And section 8, I think, of that chapter talks about electron configurations and the periodic table, because the periodic table is actually a very wonderful resource for putting together electron configurations if you understand the way it is laid out. And hopefully you guys will gain a better appreciation for the periodic table from this chapter already. And finally, the final section will be on, for elements, electron dot symbols. And actually, I think there's a, let's see. Yeah, that's the final section of this chapter. So that is what we plan to cover tonight, hypothetically. So let's talk about atomic theory first. And feel free, guys, to ask questions because if we were lecturing in person and if we have a conversation in lab, I want you guys to feel free to be able to ask questions and interact with me. I'm not here to just give you a monologue. Atomic theory was proposed by, I believe it was a scientist by the name of Dalton. I used to love to teach the history of chemistry in these courses as well, but we just don't have the time. And in an intro course for people who aren't generally going to go off and become chemists, I don't like to, quote unquote, waste your time. It's important for you to know, and it's fascinating, but I sometimes get responses from students as less than excited. So atomic theory breaks down into the following. All matter is composed of atoms. Essentially, that is an important statement, because how do you define what matter is made of? Well, we start by saying matter is made of atoms. We'll get into what atoms are made of later on in this chapter. Atoms of a specific element differ from atoms of another element. Now, there are two options. There are two general values of an atom that we can discuss. One of those, and we will come back to these, I think, in the very next section. The first value that we would be talking about is the atomic number, which is very conveniently symbolized by the letter Z. Yep, I know, it makes total sense. You can look at atomic number and see where the Z is. And keep this in mind. This will be equal to the number of something called a proton, so protons in the nucleus. And I am adding this to this section so that you guys have time to absorb it in multiple moments. The other number is what we call in this book, the mass number. Sometimes gets called the atomic mass. The mass number is the number of protons plus the number of neutrons in the nucleus. Now, what are protons, neutrons, electrons, even? We will come to that if you are not familiar with these terms, and that is okay. This is an introductory course. Now, the reason I put these two values up here, atomic number and atomic mass, well, we're under the subheading of atoms of a given element differ from atoms of another element. These are the two options that you have, or some aspect of these two options that could cause that differentiation between atoms of one element to another. And I'm not going to give you the answer to that yet. Please ask your question.
So for mass number, it's the number of protons and neutrons, or is it the number of protons plus neutrons?
So it's the number of protons plus neutrons, which is technically the same thing as saying the number of protons and neutrons. It is technically the same thing. If I were to say I have X number of carrots and X number and Y number of peas in a bag, that would be a summation, correct? So yeah, they mean the same thing. Good question though. I appreciate you asking.
Thanks.
And thank you for making use of the hand raise option. That got my attention.
Thanks.
Any other questions, guys? Okay, then number 3 for atomic theory is that chemical compounds, which we talked about in chapter 1, or we didn't have that conversation, but you guys read about and have videos available to you on, and I can return to if you so desire. Chemical compounds consist, I'm saying are equal to, or consist of, yeah, I'm just going to use an arrow instead. They consist of integer, meaning whole number ratios of atoms. And the reason I like to define it specifically in this fashion, the reason I've chosen my wording exactly like that, is to emphasize that you cannot have parts of atoms in a compound. There is no H2.5O. There is no O3/4. There's always going to be, for example, O2 or H2O or CO2, so on and so forth. I could go on and on. C6H12O6, C6H6. There's so many compounds out there, especially organic compounds, but there are a huge number of compounds out there. And they're always built of whole atoms. So the ratio of atoms will always be a whole number. And finally, when we're talking about atomic theory, the fourth item on the theory is that reactions change only the arrangement of how atoms are combined. Now, that is not entirely accurate. There are reactions where technically the arrangement of atoms does not appear to shift. We will talk about that later in this class. This is a rule that gets broken. So this fourth one in particular this rule gets broken when talking about some types of reactions, and I will return to that. And that is a fun thing to return to, and it is an important thing to return to. Okay, so that is atomic theory. Any questions? Okay, I'm going to keep moving forward then. Is this pace working for you guys? Okay, fantastic. Moving forward then, now we're going to talk about the next section, which is in the book, it's called the section on elements and the atomic number. That's the next subsection in the book that we are going to look at. Actually, you know what? No, I'm wrong. My apologies. We haven't gotten there yet. I'm following my own outline. And so I should mention a couple of other things still under the section 2.1. So we're still under section 2.1, but we've moved on from the initial aspect of atomic theory. So atoms are neutral. The question is, what is the rule? The rule that I said that was being broken is the rule about reactions change only the arrangement of how atoms are combined. And that is the rule we're talking about. That's the one that gets broken. Okay, don't worry too much about that. We will come back to that at the appropriate time. Okay, so atoms are neutral. They get called the fundamental, you could call them the fundamental single building block of elements is essentially what you could think of them. Some people call them particles. I guess you could call them particles. They are a type of particle. So atoms are the fundamental particle of elements, you could say.
Professor, is this one still a part of the atomic theory?
So what I'm talking about right now is not a part of atomic theory itself, but falls under the section in the book about atomic theory.
Okay, thank you.
Yeah, no problem. The atomic theory itself are that list of 4 essential components that I numbered off for you, that all matter is composed of atoms. Atoms of a given element differ from one another. The chemical composition consists of whole integer ratio. I'm sorry, I've got some sort of insect that's deciding to buzz around me right now. It's one of those days, isn't it? Okay, so chemical compounds consist of whole integer ratios of atoms, and the 4th one being the one that I said gets broken sometimes, which is reactions change only the arrangement of how atoms are combined. Okay, so now we're talking about some things that come out of that original atomic theory and the discoveries associated with that atomic theory and the things that we've learned since then. So we know out of that theory that atoms are the fundamental particle of elements. So if you remember that elements, hopefully you guys remember the definition of an element, but let me see here for a second. I know I wrote that down somewhere. Make sure I got the specific definition. And sometimes I come up with my own definitions and those can confuse people because you guys aren't in my head with my own form of shorthand. Remember that essentially the book defines, and not just the book, but we define an element as the fundamental pure substances it cannot be broken down further. That is to say that when you break apart compounds, compounds can be broken down further because they are made of different elements. But an elemental substance, or if you went with an elemental compound, you could break it down furthest into just atoms of the element. Because the element is the fundamental pure substance that cannot be broken down further. And atoms are the individual particles of that specific element. Every element has its own atoms, and every element can be broken down into atoms, but you cannot break those down further and still call it matter the way we generally define it. Any questions about that? Okay. If that is clear, then let's talk more about the question, well, okay, if atoms are what pure elements are made of, then from there, we can ask, what are atoms made of? So, all right, what are atoms made of? And I kind of wish that I was doing my historic lecture, my chemistry history lecture, because that is fun and so interesting to look at about how they discover these things. But anyways, there are 3 fundamental subatomic particles that are the building blocks of atoms. So if atoms are what compounds are made of, atoms themselves are built up of subatomic particles, okay? And there are 3 subatomic particles, precisely, as someone just said in chat, protons, electrons, and neutrons. So these 3 subatomic particles are our protons, electrons, and neutrons. So let's talk about these particles. And I'll just make a little table here. So we'll talk about the particle. We'll talk about, why not talk about the symbol often used to represent it. We'll mention the mass of these particles. And we'll talk about the charge. And then after that, we'll talk about the location, because of course that's important as well, where these things actually located. So the particle, we've got the proton, we've got the neutron, and we've got the electron. Symbols, P, N, and E minus. Mass, for the proton has a mass of 1.672622. You don't have to take it out that far. Your book puts it in grams. Because I tend to like SI units, I'm actually going to put it in kilograms, just also to give you guys a little bit more variety. Times 10 to the minus 27 kilograms. Now, before we even go any further, I have a question for you guys also about this. Does anyone know how much the conversion, well, what the conversion is between kilograms to pounds is? Is anyone familiar with that conversion? You don't need to be. And here, living in the United States, most people tend not to be. So that's okay. Put it right up here in a very inconvenient location. 1 kilogram is roughly 2.2 pounds. Okay, so 1 kilogram is about 2.2 pounds. So based on that, you could say that a single proton weighs roughly around 3.2 to 3.3 times 10 to the minus 27 pounds. Just to put it in terms that people in the United States tend to be a little more familiar. Okay, so if you're thinking about your 10-pound barbell you might lift, or your own weight, or your 500 to 1,000-pound car you tend to drive, built up of particles that are made up of subatomic particles that are times 10 to the minus 27 pounds. Think about that. Now, the neutron is very similar in mass. it's 1.679, and you can look up the rest of that, times 10 to the minus 27 kilograms as well. And I put it in blue because that happened to be the pen I was using, as well as it's interesting to make it stand out and look at the difference there. The electron is significantly smaller than both of these. It is 9.11 times 10 to the minus 31 kilograms. Very, very tiny, even compared to the proton and neutron. Finally, talking about the charge of these particles, we tend to say that the proton has a single positive charge. The neutron is neutral, so it's got 0 charge, and the electron has a single negative charge. Okay, so these are the particles that make up atoms. These are the things that we need to combine in some way to make an atom. And we will also talk about in this chapter where these particles are located within the atom. Are there any questions thus far? Okay, cool. And I do appreciate you guys letting me know. Is this going too slowly for you guys? Okay, cool. Good, good, good. I'm going to avoid making any drug-related jokes because I once made a joke about how I needed to do some of an illicit substance, and someone actually thought I was actually consuming a substance when I have never in my life. So I know I'm a boring individual, okay? I'm very dull. But I actually got accused of consuming things. So no, I'm not going to make a joke that, especially on a recorded lecture, that could then end up as a meme on TikTok. No, thank you. This will already probably become a meme on TikTok. Okay. Yeah, not the way I want to be famous. Thank you very much, though. I'd rather be known for my music and being lead singer of a band than some sort of reject teaching chemistry.
Wait, are you saying you're in a band?
I'm saying that I used to be in a band. Yes.
Nice.
We'll talk about that some other time. Staying on topic. Okay, so subatomic particles, we have mentioned their general characteristics. Now, what else did I want to cover in this section of the book? Let's just talk about the location and the structure, the general idea and the structure of an atom. That's because science teachers are capable of being awesome. Not all science teachers are awesome, but they are capable of being awesome. And they are also typically tending toward being multifaceted and very talented. Again, I'm not even necessarily talking about myself. I'm just mentioning as a general group of people that I might be associated with in some general fashion. So I think that is where that brings us to the general structure of atoms. Now, this is not how I want you guys to picture atoms. It's just the general rough idea of how atoms function. So there is the nucleus at the center of an atom. And then surrounding the atom are something in what we call orbitals. Not orbits, orbitals. Now there's a reason why there's a different word used. These are not orbits. because the structure of an atom is not like that of a planet being orbited by moons. It's not the same as the structure that we see in celestial astronomical situations. They are not the same. They often get used as analogies, but that is an incredibly huge disservice to quantum mechanics and a huge disservice to what is actually ongoing in the atoms that we are made of. So in the nucleus, are protons and neutrons, and the electrons are in those orbitals that surround the nucleus. So they exist, the electrons exist in a orbital cloud, in clouds of orbitals that surround the nucleus. And there is a huge amount of space or distance between the nucleus and the electrons themselves. There's actually generally a huge amount of space between different atoms. Most of the space occupied by matter is actually empty space. So if someone calls you a vacuous, empty being, just take it as a compliment. They're saying that you are made of matter, and that's all there is to it. You're just something made of matter. Thank you for that. Moving on. Now, are there any questions about this? So what is the maximum number of neutrons and protons in a nucleus? That is a very interesting question. So the question that was asked is, I guess you guys can see it, but that is an interesting question. To be stable is assumed to be somewhere close to, what is beyond 91? So let's answer this with a number of facts. There's the fact that there is currently, people tend to say, according to the book at least, there's 118 what we call known elements on the periodic table, of which approximately, I think we tend to say, not even approximately, they tend to say 91 are naturally occurring elements. Now the 91st element is not even something that I would necessarily consider something that should be the limiting element. So it is not necessarily, I definitely need to double check my notes elsewhere about what those 91 naturally occurring elements are, because the 92nd element is uranium. And I promise you that uranium is a naturally occurring element because we mine it. We go digging for it, and people definitely refine it. We will just say for peaceful purposes, for power generation, because fission can be used for power generation. Although, of course, I don't think most people tend to realize that that power generation is still converted to electricity utilizing a steam-powered engine. We still use steam engines in your nuclear reactors. All that that nuclear reactor is doing is heating the water. So keep that in mind. Same thing goes for a coal burning plant. Same things goes for a oil burning plant. You literally, you essentially are driving a steam engine. Okay. Don't hold me to that, of course. I am not a specialist in power generation. There may be more details to that, and I may be completely inaccurate on that. Moving forward, to answer that question though, the highest number of protons and neutrons that we have been able to put into a nucleus is a nucleus containing 118 protons, because 118 is the atomic number. And looking at my periodic table that I have behind me, I don't actually have the mass of that thing. Let's see if I can pull up the periodic table on the internet then. The periodic table that I have behind me is older than I thought. So 118 takes us to well, it's not a question that's incredibly important, but let's just even look at number 103. 103 is not a bad place to start, okay? 103 is the number of protons. That's the atomic number. The atomic mass of that thing, the atomic mass is 262. And based on what I told you about atomic mass and atomic number, so if this is the atomic number, then we know that we have 103 protons, and then the number of neutrons is going to be 262 minus 103. And if you guys are following, you know that this is going to be what? Well, it's going to be 100, and I would say 50, not like written like that. Let's try writing it correctly. 159 would be the appropriate, correct answer to how many neutrons are in that particular element. Now, at 118, I suspect it's even higher for the number of neutrons, because the number of neutrons in a nucleus is generally higher than the number of protons. It generally exceeds by at least a few. Good so far? Does that answer your question? Okay. So, and no, you don't need to know that fact for the test. That is a little bit more detail than you would need to know. Now, when it comes to talking about orbits versus orbitals, let's explain the difference there. Okay. An orbit is generally a 2D regular, it's either going to be circular or elliptical, something like that. It's going to have some sort of regular roundedness to it that tends to be defined in 2 dimensions, and it's going to orbit or circle something specific at the center. Okay. So it's a 2D regular movement around something else at the center. That's an orbit. Electrons don't orbit. Celestial bodies orbit, and there are other jokes that one could make there as well about this or that orbiting things. However, electrons don't orbit. So what is an orbital? An orbital, well, let's get this right the first time. Let's not just make up things in my head. An orbital, essentially, Google is defining orbital as a duo in music, which is not the same thing as atomic theory. An atomic orbital is a mathematic function describing location and wave-like behavior of an electron in an atom. Okay, it's a 3-dimensional probability function. So essentially, an orbital is a 3D defined by function, area, and space, where an electron can be found. So unlike an orbit, it's got a third dimension to it. The easiest way to think about that is if we were look at the hydrogen atom. So the H atom, the hydrogen atom, the most simple element of all, has just a proton, the most simple form of it, and we'll come to variations on this, but the most simple thing has a nucleus with one proton and only one proton, no neutron. That's the nucleus. Then you have one electron that is orbiting in that is in an orbital, a three-dimensional orbital, three-dimensional defined space surrounding that proton. And I say three-dimensional because it doesn't mean that it's going to move in a plane. It moves within, drawing a three-dimensional object is very hard to do in 2D. But if you did like a cut into, if you imagine like cutting into something like this, like if we were to cut into a sphere, for example, because the first type of orbital is spherical, then the orbital that that electron exists in is three-dimensional, and there is space where it moves up and down, left and right, in all three types of spatial directions that you can define. It is not limited to just moving in an XY plane. It moves X, Y, and Z. Any questions about that, guys? Let's see what the chat says. Let's see, orbitals are able to be predicted. The shape of orbitals can be predicted, yes. The movement of the electron within the orbital is very random. That's why we say it's a probability function to let you know where the electron could be. It doesn't actually tell you where it is. I can go back to the previous page, absolutely. 1 second. The previous page looks like this. So yeah, orbitals, the shape of orbitals are predicted by the quantum mechanic functions. The location of the electron can be said to be within this finite space known as the orbital, but you cannot generally locate the electron perfectly. Well, we can say that you could locate it perfectly, but if you did locate it perfectly, you would not be able to know what speed it was traveling. And that is yet another thing we'll come to, I think, in this chapter as well. It's known as the Heisenberg uncertainty principle, which has nothing to do with Breaking Bad, or it has nothing to do with methamphetamine. Let's just be clear on that. Heisenberg is the name of a character, yes, but is not the name, not any relation to the scientist who came up with Heisenberg's uncertainty principle. Okay, so going back to our current slide. Now, orbitals are defined spatial regions, three-dimensional spatial regions with an XYZ component each to it that tells you generally where electrons will be located. They're a probability cloud. You can think of them as a probability cloud. That's another good word associated with orbitals, is probability clouds. Okay. So electrons are located within these probability clouds. Questions thus far? Okay. then let's continue kind of following the general pace of the book. And we'll say that in the book, the next thing that they kind of cover is the atomic number and the atomic mass. So let's talk about atomic number in a little bit more detail. We said that atomic number is the number of protons in the nucleus of an atom. Okay, and let's add to that a few other kind of tangential facts. The attraction of the negatively charged electrons to the positively charged protons is what holds them in the orbitals. Just as you have gravitational force that pulls moons and holds objects in their orbits surrounding celestial bodies. So it is gravitational attraction, gravitational force that holds the Earth in orbit around the sun. It is the attraction, the electronic force between the electron and the proton that holds the electrons in their orbitals. Okay. This is essentially in part 2. This is part 2.2 because we are talking about chapter 2. Chapter 1 is essentially covered in a module on the lecture site, and I am doing my best to move on to chapter 2 so we can keep pace and make sure that you guys learn everything you need to know for this semester. Because even if you are not becoming a chemist, chemistry will be a topic, and there will be a number of things I need to teach you this semester that will at some point show up in your education if you are doing something at all related to the sciences. Yeah, no problem. You got it. So the attraction of the negatively charged electron to the positively charged protons is what holds them in orbit, in their orbitals. I don't want to use the word orbit. I want to say in the orbitals. Neutrons don't directly have any effect on that because remember, neutrons are neutrally charged. Now, please, if there is one thing you do learn from this class, one of those things I hope is the charge of these particles. Please, on the exams, don't, if I ever ask you, what is the charge of one of these particles, answer in a different fashion than the correct answer. Protons are positive, P goes with P. Neutrons, like the beginning of the name indicates, is neutral, and electrons are the only other option you have. It's negative. Okay, so this also means that neutrons don't affect electrons. That's something to keep in mind. Now, why am I bringing that up? Well, we're talking about the atomic number is the number of protons in the nucleus of an atom. What I want you to think about then is protons are what define an atom as being of a specific element. That is to say that the defining subatomic particle of a game you could play, which is guess what element this is only determined by the number of protons, which means at the same time, the atomic number. If you know the atomic number, you know the number of protons. If you know the number of protons, you know the atomic number. If you know either one of those, you also know what element you are talking about, because the protons in that nucleus make that atom a specific element. No two elements have the same number of protons in their nucleus. All right, guys, I'm going to take a break here for just a few minutes. I'll be right back. I'm going to pause lecture here. I'm resuming recording. Let's see what the questions are that we've got. You should teach Chem 400 too. Yes, and I have taught Chem 400 before. I've taught Chem 400, I've taught Chem 401, I've taught Chem 306 as well as 305. I've taught biochem, I've taught physics, I've taught calculus, and thank you. I appreciate that. So yeah, the last part said that neutrons have no effect upon the electrons, and that's because they're of neutral charge. And the only way that you really have an effect on electrons generally is through the use of a charge, be it positive or negative. Now, that's not completely the only way. If you've ever taken any sort of physics or physical science, you may have learned that there is a connection between electricity or charge and magnetism. And yes, it is exactly correct. There are direct connections between electrical fields and magnetic fields. Direct link. That's why light is a form of electromagnetic energy. Now, outside the scope of this course to some degree, but it's an important thing to keep in mind. So let's see where we were going with protons are what define the type of particle that the protons are the particle that define what an atom can be defined as when it comes to its type of element. So that is very important to keep in mind. That means change the number of protons in a nucleus, and you change the element that the atom belongs to. And when it comes to that, here's an interesting thing to keep in mind. Different elements have different physical, or can have very different physical and chemical properties. Okay? So what that means is the number of protons determine the physical and chemical properties of an atom. If you change the number of neutrons, the only thing you might change is you may change the stability of the atom. You change the number of neutrons inside that nucleus, and you affect the stability of the atom. You don't have any way of changing the element that that atom belongs to, but you can change the stability of it. This is the origin of radioactivity. If you change the number of electrons surrounding the nucleus of the atom, you change a neutral atom into a charged particle that is known as an ion. Okay, so if you change the number of electrons surrounding the nucleus of an atom, it becomes an ion. It is still a type of particle related to an atom, but we tend to call, when we're talking about atoms, we tend to be talking about neutral particles, whereas charged particles that have lost or gained electrons become called ions. Any questions?
Professor,
Yes.
that word, so it says into changed, is that particle?
Into charged.
Charged?
Into charged particles, yes. My handwriting does tell you a little bit about my familial history. And what it tells you is that there were doctors in my family. I can't quite write bad enoughly to be able to write prescriptions, but I am approaching. Okay, other questions, please. I'll wait a few seconds to see if you guys have questions. And if there are no questions, I'm not even going to wait to see if you guys respond, just because I don't want you guys to feel like you have to actually even just nod your heads or anything like that. I'm just going to move on. I'll pause occasionally for questions. Okay. And this is actually going to become the lecture that goes up on Canvas for these sections. So I'm very glad you guys are participating. That also means on Thursday, I'm going to give another portion of the lecture. And for this time period, I think it's a very good use of both your time and my time. So there is another type of particle that we should talk about. So I mentioned, and we'll reiterate this, what happens when you have atoms with the same number of protons, but different number of neutrons. Now, based on the previous slide, you would safely arrive at the idea that it might destabilize or stabilize the particle depending upon what is the optimal number of neutrons inside the nucleus of a specific element. But there's also names for these things. So let's break this down into detail. You are still looking at atoms of the same element, but we still need a name to give these things. Because you have changed something about them. But by changing the number of neutrons, you alter the mass and weight of the atoms. So you don't change the element. They have very similar, they will have essentially the same chemical and physical properties for the most part, but the mass and the weight therefore will differ because you have increased or decreased the two largest particles that are inside an atom. Remember, protons and neutrons are about 1,000 times larger than an electron. So electrons are negligible when it comes to the mass or weight of the atom, but you change the number of neutrons, you are basically capable of altering the mass significantly. Good so far. Okay, so what are these things called? Well, the name that we use are isotopes. And so let's define isotopes. Isotopes are atoms of the same element with different atomic mass. And therefore, this means different number of neutrons in the nucleus. Okay. And that is important because this has all sorts of effects. Like we said, stability is one of them. And the stability is the origin of radioactivity, which tends to be something that we have some concern about because exposure to significantly radioactive substances might be something you want to avoid on average. I'm not a big fan of sitting around radioactive substances. If you need an extended examples of that, just look back at it around, I think, right when radioactivity was becoming a part of pop culture, people didn't realize how dangerous it was. And so radioactive compounds were actually readily available. You had radioactive watches that people were wearing because they would glow in the dark. You had radioactive makeup that people would be putting on. You would have radioactive toys that children would be playing. And for most people now, when you typically understand the dangers of radioactivity, based on, if nothing else, your experience with movies and history, because you may know a few things about what we have horrifically applied radioactivity to. I don't have to go any further than to think about items that have been dropped horrifically on cities, and I don't want to go there because that's a very sad topic. But anyways, radioactivity is a serious thing to think about. And it is the second to last chapter in this course that we will discuss. So I'm not actually going to go into radioactivity right now. However, let's talk about another effect these can have. The weight can affect the reactivity of things in small atoms. And this is a topic that your book, I don't think, actually covers, but it is fascinating. So the best example of this is if we talk about isotopes, for example, of hydrogen. So hydrogen being such a simple element and such a heavily studied element has, we know of three, we could say, relatively stable isotopes. Two that are stable and one that is radioactive. So let's see here. So in the previous slide, we said weight can affect the reactivity in small atoms. reactivity in small atoms. Thank you for asking. I don't mean to move too fast, but I also do not want to draw out lecture because my goal tonight for you guys is to wind down at the very latest by 8:30 tonight. I would love to have tonight be in the early evening for both myself and you guys. That is my absolute goal here, okay? So that you guys get to get a lot of good information from me, and at the same time, you get to go home not feeling like you're a stuck captive audience. Hopefully you're already at home, but wherever you are, this lecture ends early enough that you're not sitting there going, well, shoot, I missed my favorite episode of The Late Late Show. Because everyone loves, no, James Corbin doesn't host The Late Late Show. It's the, which one is it? I don't remember off the top of my head. Anyways, moving on. So the two stable isotopes, there's one that has just one proton and no neutron, because if you look at the periodic table, the atomic number of hydrogen is 1 and the atomic mass is close to 1. Now we'll go into why that is as well, why it's not exactly 1. But anyways, it's 1 proton, no neutron in the most common form. And this is the most common form of hydrogen. And it is, in my opinion, conveniently named protium. And now the spelling of protium, of course, is completely eluding me, which is annoying. Let's see, is that the correct spelling? Yes, that's it. Okay, protium is Protium. Yes, exactly. Protium. And this one consists of 1 proton in its nucleus and 1 electron in its orbital. No neutrons. Now, the other stable has 1 proton, 1 neutron, and this is also stable, and it'll have also 1 electron. Yeah, I guess you can say here, this also has 1 electron, 1 electron. And this is known as deuterium. And finally, the radioactive form has 1 proton, 2 neutrons, and 1 electron. And this is known as tritium. Okay, so this is useful because it shows you examples of an isotope. And this also breaks down into something that I wanted to tell you about, which is think about these things. So protium has an atomic number. For protium, atomic number is 1. For deuterium, atomic number is also 1, because remember, the atomic number for an element, for atoms of the same element, the atomic number is always going to be the same. So deuterium, tritium, and protium all have the same atomic number. But when we jump over to looking at the mass number, which is capital A, it has a mass of 1 versus a mass of 2 versus a mass of 3. So remember that A is the mass number and Z is the atomic number. Now, what does that mean? Well, with particles as small as hydrogen atoms, you can literally see this happening with these numbers. The mass of deuterium is twice the mass of protium, and the mass of tritium is 3 times that of protium. So now, because tritium is radioactive, it's not something typically that you would want to have around or near living organisms, but deuterium is not radioactive and it's stable. So for that reason, deuterium, at a first approximation, you go, well, it's not radioactive, it should be safe. But it's not. Deuterium is actually poisonous. Deuterium is poisonous because of its mass being twice that of protium. Because the mass of deuterium is twice that of protium, it has a significant effect upon the rate, the speed at which chemical reactions occur. And I'm not going to just say that it doubles it, because the rate at which a reaction occurs gets more complicated depending upon how the reaction is happening. The kinetics, or the study of rates within chemistry, is more complex than just saying, well, the mass doubled, so therefore the rate doubled. Not necessarily. But for the most simple reaction, it does double the rate of a reaction. And that is a problem, because if you double the rate of a reaction, you slow significantly. You're not doubling it, sorry, you're halving it. I need to correct that. You are halving the rate of halving, dividing in half the rate of a reaction. And when you cause a reaction to slow by half, that could be something that is so significant that it could kill an organism. Keep that in mind, because that alone is something very fascinating to think about. Okay? Any questions about this? Okay, if there are no questions, then I'm going to keep moving on, because I've actually spent a little bit more time on that specific example than I wanted to, but I do find it really interesting myself. So a few other things. Let's see. To begin with, we'll talk about this later, so I don't want to spend a lot of time about it, but I think it's chapter 11, radioactivity, and also talking about things with isotopes. There is a technique in chemistry and physics known as, of course, radioactive carbon dating. So, and you can do that not just with carbon. Depending upon what you're studying, you might need to use a isotope of a different element, because the half-life of carbon is only, so the half-life of the specific isotope that people look at, which is carbon-14, is roughly 5,700 years, which means the radioactive carbon dating is actually only useful for dating things plus or minus within that time frame. You can't actually go out thousands and thousands of years beyond 5,700 years. You actually have to use other elements. And that's important too. When it comes to radioactive dating, there's also stable isotopes can interact or not interact with magnetic fields. So if you guys have ever heard of nuclear magnetic resonance, which is a technique that you can look at the magnetic properties of nuclei, and in relation to that, you can do some imaging from that, which is magnetic resonance imaging. Have any of you ever had an MRI? Has anyone ever had an MRI done? You got to be at least one person in here who's had an MRI. I can't be the only person who's got to lie inside a giant tube and listen to knocking sounds. Classic joke stated by, I think it was Yogi Berra. He said, the doctors checked my head and found nothing there. Of course, he was trying to say nothing wrong, but what he ended up accidentally saying was that he had no brain. But what I'm trying to point out here is nuclear magnetic resonance, which looks at the magnetic properties of nuclei, and that depends upon a whole lot of things that I don't want to go into specifically, but some isotopes of an element are magnetic and others are not. So they can give you certain compounds that have been loaded with an isotope that is magnetic or one that is not magnetic to allow them to then change how they are able to detect these things utilizing the magnetic field. Of course, it's called magnetic resonance imaging because whenever people see the word nuclear, they freak out. They go, nuclear means radioactive. And that is not true. Nuclear does not mean radioactive. Nuclear simply means associated with the nucleus. Nuclear simply means associated with the nucleus. Radioactive is what means radioactive. Exactly. That is precisely why they give you an injection before the MRI. Yes. They are loading you with substances that are going to allow them to change how the magnetic field interacts with the same substances in your brain. They're just going to be loaded now with the isotopes, which then alter the interactions of those compounds based upon the atoms themselves with the with the magnetic field. And no, it doesn't mean that you had a radioactive substance inside of you. It just means magnetic imaging and looking at isotopes, nuclei that are isotopes of each other made it possible to look at something that might be related to your health. Really cool, not dangerous, very useful. Boom. Okay, let's see. Where are we time-wise? Time-wise, we're doing okay. We talked about isotopes and some of the interesting examples of those things. And I like to share these things with you guys because I'm hoping that if you have a better understanding of the science, there'll be less fear out in the world. And you might even share my excitement for the technology that we're using, share my excitement for understanding the technology. It's not just a magic box that knocks at you anymore. You now have some concept of what's actually going on in there. Okay, so now the actual atomic weight is not the same thing as the mass number. And I should make sure that I use the mass number versus atomic weight very specifically. The mass number is the number of total subatomic particles in the nucleus, and the atomic weight is the weight of an isotope calculated, well, if we're talking about the atomic weight of an isotope, it's so if we're talking about the atomic weight of an isotope is calculated based on the weight of protons total plus the weight of neutrons total. So the weight, the atomic weight of an isotope is based on the weight of protons total plus the weight of neutrons total inside that isotope. And every isotope will have the same exact atomic weight and the same atomic number, but the atomic number, the same mass number. The mass number, though, I want to make sure we define. The mass number is the number of subatomic particles in the nucleus versus the atomic weight, which is the weight calculated based on the number of protons and the weight of them and the weight of the neutrons added up together. So one will come out in units of grams or kilograms, and the other one will not. Or you could actually do this in what we call AMU, which is atomic mass units, which is a unit calculated based on carbon 12, just for reference. Now, what does all this mean to you guys? Let's talk about that, of course. Mass number will be a whole integer. Oh, sure, yeah. So mass number will be a whole integer number because it is the number of particles, total number of particles in the nucleus, number of protons plus number of protons, number of protons plus number of neutrons inside the nucleus. Okay, so it'll be a whole integer number because it's a sum count of number of protons plus number of neutrons. If we say the atomic mass, which is a term I prefer, but a lot of people say atomic weight, it's an older term. And does anyone not know the difference between weight and mass? Because there is a significant difference. And of course, as the extreme elitist scientist that I am, I always have to mention very briefly, at least once in a semester, that mass is a measure of matter and weight is a measure of gravitational force on that matter. Exactly. Mass is how much, weight is how heavy, or how much force is being pulled. That is why your mass is the same no matter whether you are out in space, in the shuttle, on the International Space Station, on the moon, and of course, we all know people that definitely act like they're on the moon. That's a whole other issue. Mass is independent of location and other objects around you, whereas weight, it completely depends upon the closest, largest body near you. And by body, I don't just mean the other person in the room. What I'm talking about is the planet you're on, the moon that you're closest to. I'm talking about significantly large inanimate objects. Yeah, your weight on the surface of the planet is different from your weight on the surface of the moon. And of course, people often think that you are completely weightless because you feel completely weightless in outer space. Not entirely true, but you have to go into definitions. And then of course, you also have to go into What does it mean to say weightless? Well, relatively weightless when there's minimal gravitational force, et cetera, et cetera. So atomic mass being the most accurate thing to call it, atomic mass is a measure of total matter by going number of protons multiplied by, that 1 point, what did we say? We said it was 1 point. Now it's in an earlier slide. It's actually easier for me to refer back to the notes. And we said it's like 1.672 times 10 to the minus 27 kilograms per proton, plus the number of neutrons multiplied by 1.674 times 10 to the minus 27 kilograms per neutron. And so what this is actually doing, this little equation right here, this little calculation, what this is actually doing is conversion. This is a conversion. So this is taking your mass number, because number of protons and number of neutrons, right, is number of protons plus number of neutrons, this thing, and converting it to your atomic mass. This thing is a now conversion between the two, okay? The atomic mass is calculated based upon the number of particles of each type multiplied by the appropriate mass. And then you add them up and you end up with the atomic mass. So hopefully that makes sense. That's defined, it's clear. And yes, we are ignoring the electrons because the electrons are so significantly small, they generally are just ignored. When they do an exact accurate calculation, yes, they take the number of electrons into account. But for our purposes, doing it based on just number of protons and neutrons will appropriately reflect or be a close enough approximation for our purposes. So where I'm going with this, though, is the atomic mass that you see on the periodic table is not a specific mass of a unique isotope. No, the atomic mass on the periodic table is actually not the atomic mass of a specific isotope. It's different. What it is a, okay, let's say this, the atomic mass on the periodic table is a weighted average of isotopic masses. So the atomic mass on the periodic table is a weighted average of the isotopic masses of the element, I should specify, of course, of the element. So what that means is, when you're looking at that atomic mass on the periodic table, it does not relate to a specific isotope. It reflects a average, but weighted to allow you to make use of that number to the decimal ratios of the isotopes out in nature. Does that make any sense? Okay. Does that confuse anyone? Does anyone have a question about that? And if it does, you don't have to put your message in the general chat if you don't wish to. If you wish to ask a anonymous question, you can send a direct message, and I will read it back without mentioning your name and answer your question. Just keep that in mind, guys. You can always use direct messaging to reach me in an anonymous fashion, okay? Dumbing it down a little bit, that is something I shall now attempt. So, averages. The way I've always taught this is to talk about averages, okay? There are actually two general types of average calculations that you can do. This might not necessarily be dumbing it down, but this is the best effort I can make to try to explain to you what it means by a weighted average. I'm still looking for better ways, but without actually defining these two things. So an unweighted average is the type of average you learn in, let's call it grade school. And that's actually an appropriate term for everything up through high school, grade school, because when you get to college, we don't go, well, now you're in 13th grade. Now you're in 14th grade. You don't move on to new grades the way you do in actual grade school. So grade school is the appropriate term. Unweighted average is the type of average you learn in grade school. Typically you learn that possibly even as early as elementary school. It is possible. That is where you go, okay, if I have a collection of numbers like 5, 5, 6, 7, 9, 2, and 1, then you calculate the unweighted average by doing the sum of these numbers, 2 plus 5 plus 5 plus 9 plus 6 plus 7 plus 1, and then you divide it by the number of numbers, 1, 2, 3, 4, 5, 6, 7, to get your unweighted average. That's what 7 plus 14 is 21, plus another 14 is, I can do that in my head, come on. 7 is 14, 14 is 28 plus 7, of course, is 35, divided by 7, gives us an average of 5. Okay, thank you, yeah. So we're looking at an average, an unweighted average of 5. Now, why do we call it an unweighted average? It's called an unweighted average because every member of that population, that collection of numbers, has an equal contribution to the calculation of that average. There's no effect of the number of that number. Now, I know that gets confusing, so let me show you what it would be like differently. Keep in mind the number of that number. So we've got 2 5s here versus 2, 6, 7, 1, and 9. That is what I am talking about. Okay. Let's create a new population. Or actually, let's use the same one. We've got 2, 2, 5, 9, 7, 9. Yeah, okay, so we've got 2, 5, 5, 7, 9. We had a 6 and a 1. So the previous unweighted average was 5. Okay. We actually have to calculate this differently because we have to take into account what percent of the population each number is. So 5 is actually 2 out of 7. Let's see, let this actually work out right. No, this is actually going to end up giving me the same answer. Well, let's see. It should be 2 times 5 because there's 2 of the 5s. They are twice the amount. And then 1/7 of that population is a 2 plus 1/7 of that population is a 9 plus 1/7 of that population is a 6 plus 1/7 of that population is a 7. You guys follow me so far? Make sense? So there's a total number of 7 numbers. 2 of those numbers are 5. And then every other single one of those numbers represents just 1 out of 7. Good with me so far? Okay, good. If that makes sense, then we're doing good. If it doesn't make sense, please let me know because I would want to clarify further, of course. But the point I'm trying to make is this is very different from what we did before, okay? Now, or at least it should give me a different answer. I guess we'll find out. Here we go. I'm grabbing my calculator because I don't feel like doing this in my head. 1 divided by 7 multiplied by 5. Sorry, 1 divided by 7 multiplied by 7, of course, is going to give me 1. Then we are going to get 1/7 times 6 plus 1 divided by 7 times 9 plus 1 divided by 7 times 2 plus 1 divided by 7.
You forgot the 1.
Haven't gotten there yet. Times 1 plus, I forgot to write it out. I got you. Thank you. Plus, of course, whoops, I don't know why the color changed. That's a fun one. Thank you for pointing that out. I want to make sure my examples are perfect. Yes, there should also be a plus 1 divided by 7 times 1, because every member of that population does contribute to the final answer. Exactly. So it should finally be 2 divided by 7 times 5. Now, if I do that, I do not get a different answer. That is problematic. Let's see, what am I doing? Nothing, there's just a flaw in my example. That's the problem. Yeah. There's a flaw in my example. That's the problem. Let's see here. Yes, this is an example of a weighted average. This calculation is the general idea of what you would be taking for a weighted average. And the reason for that is it's weighing the respective items based upon how much they are present within the population. Now, it turns out that this weighted average is essentially going to give us the same answer, unfortunately, I think. I say unfortunately because I was hoping my brain would come up with a different answer, a good enough example where the weighted average and the unweighted average are different, because they don't always have to be. Let's see. 10 divided by 7. Of course, now I put myself on the spot when I start making up examples. Okay, let's just actually do this. 1.42. 2 divided by 7. 0.28. 9 divided by 7 is 1.28. And this, of course, is 1/7, which is 0.14. This is 1. 6 divided by 7 is 0.85. So 0.85 plus 1 plus 0.14 plus 1.28 plus 0.28 plus 1.42 is indeed very close to 5. Yeah, exactly. So that is what we are going to be getting. The key I wanted to make here is this is how you lay it out in general for a weighted average. Now, the difference between that sort of weighted average and the sort of weighted average for an isotope is you use a decimal ratio related to 1. And yes, I can I'll go back here. So the weighted average here is the weighted average. So the example is with the fractions, that's the weighted average. And not all weighted and unweighted averages will give you different answers. But when you use a weighted average that is weighted as a percentage, it will give you a completely different answer. Okay, you guys ready to move forward? Okay, so an example of this. Let's see. I think there's even a good example. Yeah. I'm just going to pull one of the examples from the book that you guys can easily review. And that'll also make sure that I don't do something goofy that gets even more confusing. So for isotopes, to begin with, the calculation is done. The average weight or mass, the average mass or weight of an atom is set up as the sum. In your book, they use this, the sum of the percent as a decimal of the isotope in nature and we use the decimal because you can't actually directly use the percent value in a calculation. You cannot use percentile values directly in a calculation. You must use the decimal representation of that, and you multiply it by the mass, or the atomic mass of, let me correct that, I didn't give enough space, the atomic mass of the isotope. And the sum means that you do this for every single isotope that is naturally occurring, and they will all have different ratios. Does this make sense? Okay. If there aren't any direct questions about this little formula, then I will show you guys an example, because the example, of course, helps tie this together and really show you how to utilize it in a more direct fashion. It's not useful to just look at a formula. Okay, so I'm going to utilize the example that is given to you guys on page 47 of your book. This is where, right below the formula even, where it is written, they're talking about calculating the average atomic mass of chlorine. Utilizing the two most stable, most common isotopes of chlorine. I suspect there are more than just two, but they're using the most stable two and largest, most abundant. The average mass of chlorine. And so the isotopes we have are chlorine 35, and I'll explain this to you guys in a second. I realize I omitted the use of that symbolism. Chlorine 35, which has a mass equal to, it is, chlorine 35 is 34.97 atomic mass units. The mass of chlorine 37 is, let's see, it's 36.97 atomic mass units. And we can say the abundance, which is just another way, fancy way of saying the percentage of these in nature, are for chlorine 35, the naturally occurring abundance is 75.77%, whereas chlorine 37 has a abundance of 24.23%. So this calculation then comes down to the average is then equal to converting percentile into a decimal. You of course move the decimal place 2 places to the left. So you get 0.7577 multiplied by 34.97. This is for chlorine 35. And then we add to it, this is an AMU. Percentage doesn't actually have a unit. Then we look at the abundance of chlorine 37, and it is 0.2423 multiplied by the mass, which is our 36.97 AMU. Do this calculation in your calculator, and you will get the answer of 35.45 AMU, which is the answer of what you will see on the periodic table. Now, AUG, I'm actually writing, you mean this right here, the AMU? Oh, the average. This is average, yeah. This is shorthand for average. If you prefer, very quickly, I can say Average. There we go. Yeah, no, I know. My handwriting is actually a lot better than this, but when you try to utilize a Wacom tablet or any sort of other computer tablet with a pen, it's actually more challenging than people realize. My handwriting is actually phenomenally good compared to what I've seen some people do with these tablets. Okay, it's okay to be confused. Allow me to explain and give you a little bit better of an example. So in the time that we have left, I think I will try to do another example primarily. So, of course, first is the side note. Isotopes are represented by the atomic symbol, and then you put in the upper left-hand corner the mass number of the isotope, where the X is the elemental symbol. That, I hope, makes sense. That is where I was getting the chlorine 35 versus chlorine 37. Or from our previous example of isotopes, hydrogen protium is H1 versus deuterium is H2 versus tritium is H3. Okay, hopefully that makes sense. Now, that of course is not directly helpful to helping you guys understand the averages. It just helps you understand what I'm writing quickly. So let me see if I can explain first the example here. Okay, this right here, this is percentage converted to a decimal. These things right here are the percentages converted to a decimal. And this thing right here, these are the atomic masses of the isotopes. And we multiply the ratio for chlorine 37 versus the ratio for chlorine 35 to, sorry, well, that doesn't help if I reverse these, my apologies. This is not 37, and this is not 35. I actually assign them to the correct ones. That will be less professor confusion and more professor, hopefully, at least neutral in the right direction. So how are we doing, guys? Does that help at all? Is following me at all? Okay. Is there any confusion? Please let me know if there's confusion. Would one more example help? Okay. All right. Let me see if I can do. This is not the most difficult thing in this chapter, in my opinion, but I don't want to scare you guys off either. It is a challenging thing to get because it's a number of mathematic concepts that if you haven't seen them very quickly, then you may be thrown off. So let's see here. That brings me to example, challenging one, conceptual problems. Calculations, good problems. Okay, let's just do one that I make up. I can make up problems and they will actually work. So, okay. Let's pretend we're talking about oxygen. And these are not going to be numbers actually taken from somewhere. We're just going to make these up, okay? Actually, you know what? Let's not do oxygen because then I start drawing a lot of O's. Let's do nitrogen. At least N's don't look particularly weird. So let's say that nitrogen has, well, nitrogen does have a naturally occurring isotope of 14. Nitrogen 15 is a stable isotope that is low in abundance. 14 is the most abundant. 15 is less abundant. And let's throw in nitrogen 16 and nitrogen 19. These are just made up ones. These are not ones that necessarily would be that abundant. We're just going to throw these out there. Let's see, in chat, we just said questions might be random, but are we going to be doing mole conversions? Absolutely, in this class, yes, we will be doing mole conversions, yes. We will get to stoichiometry. Stoichiometry is a lot of fun. That's not in this chapter, but yes, we will absolutely be doing stoichiometry, don't worry. You can look forward to that. So let's go isotope. Then we will say percent, that's illegible. Percent abundance, and I'm already running out of time, darn it. All right, percent abundance, and then atomic mass. Darn, I really did set myself to an 8:30 deadline. I don't want to cheat you guys out of your class time either. I was hoping I would at least finish this topic here. All right, we're going to finish this example real quickly, and then we're done for the night. So nitrogen 14, nitrogen 15, nitrogen 16, and nitrogen 19. We'll say that 70% is 14, maybe an additional 17% is nitrogen 15. It puts us at 87%. Let's say an additional 10% is nitrogen 16. And then that leaves us a 3% for nitrogen 19. These are not real numbers, keep that in mind. That's just what we're going to go with. We'll say these atomic masses 14 is going to be somewhere around 13.89. 15 is going to be somewhere around 14.97. 16 is going to be somewhere around 15.98. And 19 is going to be somewhere around 18.94. So we set this up utilizing our formula. Very quickly, we go average then is equal to, you have to convert these every time to a decimal. So you move that decimal 2 places to the left to get that decimal value. Okay, so now we have our decimals. There's your masses. So now it's just 0.70 times 13.89 plus 0.17 times 14.97 plus, then we go 0.10 times 15.98 plus 0.03 times 18.94. You do that math in your calculator and you get your answer. I'm not actually going to spend the time to do that calculation. I will leave that final answer for you guys to arrive at. Now, does this make any more sense? I'm hoping that by seeing actually technically a more complex example, this will at least pull you a little bit more in the right direction. Okay. Okay. If you don't get this immediately, that's okay. That doesn't mean you're going to fail the class. You will still have time to get this subject and other subjects that you struggle with. As one of your classmates reminded me in office hours yesterday, there is great opportunities even for online tutoring available for you. I think it's directly associated with the Canvas website. And you should be able to click on, I think it's the link to the left of the Canvas lecture website. And there are drop-in hours, I think, from relatively in the morning to in the evening. And yes, please, what would you like to say? Daniela, please go ahead.
Oh, can I speak to you after? Or I can email you also.
If you could email me, that would be great. Yes, please.
Okay.
Thank you. I appreciate that. I will also give you guys the answer, since now we have someone asking the question. What is the answer? 0.1 times 15 points. And if you want to, Daniela, you could also direct message me. I'll try to respond to you in a direct message. So if it's a question that you don't wish to have out and about, I can do so as well, whichever method you prefer.
Professor, is that the right answer?
The answer I end up with.
19.55.
So I get, when I plug this into the calculator, I get 14.43.
Oops.
Yeah. So I get 14.43. Okay. Any other questions? Will you guys be okay if I do cut this a little bit short and we call it the end of the evening?
Wait, I still got 19.55.
Okay. My suspicion is that you're entering it into your calculator incorrectly.
Are you sure you're not entering 10.10 times 15.98? Because it
No,
does kind of look like a 1.
I'll try to put things like one by one because I put all those things together. So let me try one more time.
Okay. Thank you. I appreciate you guys not feeling like I'm robbing you of my time. I'll give you a little more of my time. I don't want to leave this conversation. And of course, I will say this again, since someone asked this last week, this is completely voluntary time. You guys are not required when I am giving a lecture like this to be present. This does also count for our lab time. And I will give you guys an additional set of assignments. I don't want to jump too much work on you, but at the same time, if this is a lab time, I do technically need to give you a lab. Those will make an appearance either tonight or definitely by tomorrow morning as a module that you guys will have at minimum a week to complete. They should not be difficult, but I will also definitely try to provide you guys with some extra support in the next few days for those modules, for that module as I post it.
Yeah, I got the answer.
You got the answer?
Yeah.
Okay, good.
So for today, the homework you just put on the canvas, right? Like number
Yes.
30 something to 50 something, right?
Yes, I think, I can't remember, I think it's about 15 questions. It is due on Sunday. And it is all from the back of the book. Yeah, and it is from chapter 1, and chapter 2 will make an appearance within the next few days as I get this lecture up and then hopefully the lecture I do on Thursday as well.
Wait, so
Yeah.
so you will post a lecture on Thursday as well?
Well, I'm going to give a lecture on Thursday for my other section. And to balance this out, since you guys essentially got I got a portion of my chapter 7 lecture, or not chapter 7, chapter 2 lecture, I'm also going to give Thursday night a portion of chapter 2 that will be recorded that you guys will get to see. Unfortunately, I won't invite you to that one because it's got to be balanced.
So we're having a recorded video for lecture on Thursday night.
Correct. You guys will get the recorded video from Thursday as well. Yeah,
And
you
then
guys are
you'll-
Tuesday class. Thursday class will get their own different lecture with different content that you guys will also be able to view. And then I will also try to schedule time, possibly tomorrow, to also, I will see what I can do. Hopefully, if I can find time in my calendar, I will also send you guys an email to be able to give an hour or 2 of lecture tomorrow that you guys can try to make it to. I'll try to balance it out that way.
Well, so today we're having the chapter 1 homework, and then on Thursday we will get another homework for that chapter.
So chapter 1 homework is completely done as far as the assignment goes. It is up for you guys, and there will be no additional homework for chapter 1 as far as lecture goes. Okay. Now, additional assignments for lab is different because lab versus lecture are different things. They are different classes technically too. They accompany each other and complement each other, but they are technically slightly different courses. Now, to address one of the questions I just saw in chat, inquiring about food policy, there is definitely no food or beverage allowed in lab. And the reason for that is we can't guarantee that the lab, even now, before any experiments are done in it for the semester, is clean without chemicals that you would want to avoid putting into your body. So having food and beverage in the classroom is not the best idea. It's bad, and it's technically bad enough when you go out to a picnic table and have your meal there and drop your food onto the picnic table, and then some people might continue to consume it. That's been exposed to bacteria, and there's no such thing as the 5-second rule. When it comes to the lab, you want to avoid that even more. Yeah, we're just looking out for you guys. Are there any other questions that I can give you? Any other questions that I can answer?
So are we having so we're having the office hours tomorrow at 3:45, right?
Correct. There'll be office hours at 3:45. And then very likely after that, I plan to, and I'll figure this out by the end of the night so that you guys will see if I do it. If I do it, there'll be a calendar schedule as well as an email sent out more than once to you guys to let you know. If I plan to do a lecture tomorrow, I'll let you know. Okay.
So another lecture, like another notes for, yeah.
Yes, because technically the way this class is set up, I'm not required to have live lectures. These are considered asynchronous lectures. However, I wanted to take this lab opportunity, when you guys were expected to be here anyway, to answer questions and give you some of that lecture time. So you had a chance to ask questions during the lecture and get it in real time.
Okay, thank you.
No problem. Anything else I can do for you guys? Thank you. I appreciate you guys understanding, and I hope that you feel my efforts to make this class accessible to you and wanting to see you succeed. Okay, awesome. Good. You've convinced me or sold me, so we're good. All right, last time. Any other questions? Yeah. Let's see, do I give you guys the name of my band? Well, if I do, then I'm at least stop it.